Okay, let's dive right into this. Welcome to today's explainer, where we're going to do something pretty incredible. We are going to build an invisible engine entirely out of chemistry. Now, if you're gearing up for the IIT JEE Main, you already know that redox reactions and electrochemistry are absolutely massive, high-weightage topics. But hey, instead of just memorizing a bunch of disconnected formulas, we're going to look at this as one continuous, totally fascinating system. We're going to see exactly how the microscopic transfer of electrons translates into the macroscopic electrical energy that literally powers our modern world.
So, here is our roadmap for building this engine today. We'll start with the dance of electrons, then move to mastering oxidation numbers, followed by harnessing electrochemical power and the math of batteries. Finally, we'll wrap up with real-world power applications. We've got a lot of ground to cover, so let's get right to it.
Section 1. The dance of electrons, foundation of power. Because honestly, before we can assemble our engine, we have to understand the fundamental fuel that makes the whole thing run.
It really is a mind-bending question when you stop and think about it. How does something so incredibly microscopic, something completely invisible to the human eye, generate the massive electrical power required to start a car or light up an entire city? Well, it all comes down to a chemical transaction, a push and a pull.
This chemical transaction is what we call a redox reaction, which is basically just a mashup of reduction and oxidation happening at the exact same time. On one side, we have oxidation, which is the loss of electrons. Picture solid zinc turning into a zinc ion by just throwing away 2 electrons. Then, on the other side, we have reduction, which is the gain of electrons. That's like a copper ion grabbing 2 electrons to become solid copper. If you ever get tripped up on this, just remember the classic memory trick. Oil rig. Oxidation is loss, reduction is gain. That is literally the golden rule of electrochemistry. Moving on to Section 2, mastering oxidation numbers, the scorekeepers. Now that we know electrons are moving around, we absolutely need a way to track them in this chaotic chemical dance. Think of an oxidation number as a hypothetical charge assigned to an atom. To track these electrons effectively for the IIT JEE, you really need to treat these rules like a cheat code. Elements in their free state? Just 0. Monatomic ions? They just take their ionic charge. Hydrogen is pretty much always a +1, while oxygen is a -2, except in a few weird cases like peroxides. Fluorine is strictly -1, no exceptions. Group 1 alkali metals are always +1, and Group 2 alkaline earth metals are +2. And the most crucial rule to remember, all these numbers must add up to 0 for a neutral molecule, where they have to equal the total charge if you're dealing with an ion.
Once you have those rules locked down, you can balance complex molecular equations using the oxidation number method. It's a highly logical, step-by-step process. First up, you assign those oxidation numbers to every single atom. Second, find what went up, that's your oxidation, and what went down, that's your reduction. Third, you multiply the molecules by whatever coefficients you need to make the total increase perfectly equal the total decrease. That way, no electrons get lost. Then, you just balance the rest of the atoms, add water molecules to balance out the oxygens, and finally, toss in some H+ ions to balance the hydrogens if you're working in an acidic medium.
And that brings us to the second technique, the ion-electron method. For ionic equations, this is absolutely your go-to method. Instead of staring at the whole chaotic reaction at once, you physically split it right down the middle into 2 distinct halves, the oxidation half and the reduction half. You balance the atoms, oxygen, and hydrogen in each half completely separately. Then, the real magic happens in step 5. You add actual electrons into the equations to balance the charges. Once the electrons lost in the oxidation half perfectly match the electrons gained in the reduction half, you just add the 2 equations back together. The electrons cancel out, and boom, you have a perfectly balanced redox reaction.
All right, Section 3, harnessing electrochemical power, the powerhouse. We've mastered the paper equations, now it's time to shift gears into physical reality and actually build our engine.
So there are 2 main types of electrochemical cells, and they are basically exact opposites. First, you have the galvanic or voltaic cell. This is your standard battery. It converts chemical energy into electrical energy through a spontaneous reaction. You hook up a wire and it just produces power all on its own, kind of like the classic Daniell cell. On the flip side, we have the electrolytic cell. This one converts electrical energy back into chemical energy. It is totally non-spontaneous, meaning you have to force the reaction to happen by hooking it up to an external battery. We use this type for things like electroplating metals or splitting water. Now, to figure out exactly which materials we should use to build our galvanic cell, we look at standard reduction potentials. These are measured against a standard hydrogen electrode, which is set at precisely 0 volts. The rule here is simple. The higher the positive voltage, the stronger the oxidizing agent. Take fluorine, for example, coming in at a massive plus 2.87 volts. It desperately wants to gain electrons. But then look at lithium at negative 3.04 volts. It's an incredibly strong reducing agent and really wants to give away electrons. By pairing a metal from the top with one from the bottom, you create a massive potential difference. And that difference is the electrical pressure driving our whole engine.
But here's the catch. If you just drop 2 metals into a solution and connect them with a wire, the reaction is going to stop almost instantly. Why? Because charges build up and choke the flow. That's where the unsung hero of the galvanic cell steps in, the salt bridge. It's a tube connecting the 2 solutions that lets ions flow back and forth. It completes the circuit, maintains electrical neutrality in both halves of the cell, stops the solutions from just mixing into a mess, and basically keeps our engine running smoothly without shorting out.
Let's move to Section 4, the math of batteries, the dashboard. With our powerhouse built, we need a way to monitor it, using some essential math to measure real-time power output and efficiency.
The single most important gauge on our dashboard here is the Nernst equation. You see, those standard potentials we just talked about, they're only true under strict standard conditions, like exactly 1 molar concentration. But as a battery runs in the real world, those concentrations change. This equation isn't just a random jumble of letters. It's the exact mathematical tool we use to calculate the real-time cell potential, represented by E, at any given moment. E0 is your standard potential, N is the number of electrons being transferred, and Q is the reaction quotient, which constantly shifts as the battery drains. I guarantee this formula is going to show up on your exam.
Next up, we have to monitor the conductance of the liquids inside our cells, our electrolytes, and they behave really differently depending on how strong they are. Strong electrolytes, like hydrochloric acid, are already fully ionized, so when you dilute them by adding more water, their conductance only goes up a tiny bit because the ions just get a little more room to move around. But for weak electrolytes, like acetic acid, adding water causes a massive, sharp spike in conductance. Why does that happen? Because the dilution actually forces the weak acid to ionize way more than it normally would, completely flooding the solution with new charge carriers.
Now, this sharp spike creates a massive mathematical headache for chemists because you can never quite measure the maximum conductivity of a weak electrolyte just by diluting it endlessly. Enter Kohlrausch's law. This law is basically a brilliant workaround. It states that at infinite dilution, where ions are so far apart they don't even interact, each ion contributes independently to the total molar conductivity. So to find the maximum conductivity of a tricky weak electrolyte, we can just mathematically add together the known individual conductivities of its positive and negative ions, bypassing that physical measurement problem entirely.
The final dial on our dashboard connects all of this straight to thermodynamics. Standard Gibbs free energy, or delta G0, tells us the maximum useful work our engine can actually do. The crucial takeaway is this formula. Delta G0 equals negative N times F times E0. Because N and Faraday's constant F are always positive, a spontaneous reaction, like one that powers a battery, must have a positive E0 cell potential so that the overall Gibbs free energy ends up negative. We can even link this cell potential directly to the equilibrium constant K, which shows us just how perfectly electrochemistry and chemical equilibrium are tied together.
And finally, Section 5, Real-World Power Applications, the Open Road. We've built the engine, we've wired up the dashboard. Now let's take these concepts for a spin and see how electrochemistry actually powers our everyday lives. Let's look at how commercial technology has evolved. First, we have the dry cell, or Leclanché cell. It's exactly what you'd find in standard flashlights or TV remotes. It uses a zinc container as the anode and manganese dioxide as a depolarizer. It's super cheap to make, but once it's dead. It's not rechargeable. But then look at the lead accumulator. This is the heavy-duty rechargeable lead-acid battery sitting right under the hood of your car. It uses lead, lead dioxide, and sulfuric acid. By running an alternator, an external power source, you can actually push the chemical reaction in reverse, which means it acts as both a galvanic and an electrolytic cell over its lifespan. But for sure, the absolute pinnacle of this tech is the fuel cell, specifically the hydrogen-oxygen fuel cell. Instead of storing the chemical reactants inside a sealed box that eventually dies, a fuel cell lets you pump the reactants in continuously. You feed in hydrogen and oxygen, they react to produce electrical energy, and get this, the only byproduct, the actual exhaust of this engine, is pure drinkable water. This exact technology provides highly efficient, totally pollution-free power and drinking water for astronauts living on spaceships. It is literally the ultimate eco-friendly application of redox chemistry.
So as we wrap up our journey today, here is your ultimate IITJEE main checklist. We've tackled the electronic concept of redox. We calculated oxidation states, balanced equations, distinguished between conduction types, utilized Kohlrausch's law, built galvanic cells, calculated EMF with the Nernst equation, tied it all to Gibbs free energy, and finally explored commercial cells. If you really understand the concepts we just went through, you've successfully mastered the syllabus for this unit. You, my friend, have built the invisible engine.
I want to leave you all with one final thought. We started out today by just looking at microscopic equations on a page, but when you look at the immense potential of things like hydrogen fuel cells and advanced battery storage, you really have to wonder, could the simple, invisible swap of an electron eventually power our entire world and replace fossil fuels forever? The chemistry is definitely already there. The rest is up to you. Keep exploring, keep learning, and I'll see you in the next explainer.